On a moonless night, when the countryside has gone dark and the air is cooled enough that your breath fogs faintly in front of you, you tilt your head back and look up, and for a few seconds you see the sky the way people saw it before street lamps, before aircraft, before telescopes gave the stars names and numbers, a pale river of light stretching across the darkness, scattered with brighter islands, a soft glow dissolving into countless points too faint to count, and someone beside you might whisper, "That's the Milky Way," as though naming it made it safe, as though simply placing it in a familiar category could hide the stranger truth that every shimmer, every dim clustering in that river belongs to a vast disk of stars and gas and dark matter, rushing around a common centre at hundreds of kilometres per second, and that this enormous whirlpool in which the Sun has quietly orbited for billions of years is not alone in the night but drifting toward another equally grand spiral called Andromeda, on a course that will one day transform the sky into a stage for the collision of galaxies. For most of human history, the possibility that entire star systems might crash together would have sounded like the ravings of a fevered mind, because the heavens were the very symbol of permanence, the dome against which human lives flickered like lanterns in the wind, while the constellations kept their shape, year in, year out. The rare comets that startled ancient observers seemed like omens, precisely because they broke the quiet regiment of stars, and even then they were treated as temporary disturbances, passing messengers rather than actors capable of reshaping the cosmic stage itself. And philosophers from Aristotle to Ptolemy built their models on the confidence that everything beyond the moon moved in perfect untroubled circles, untouched by the chaos and collision that ruled the world below. Yet even as Greek philosophers were insisting that the heavens were perfect, poets and storytellers in many cultures filled the night with dramas of cosmic battle and union, Hindu myths of universes cyclically destroyed and reborn, Norse sagas of the sky torn apart at Ragnarok, Mesoamerican legends of suns devoured and remade. And although none of these tales were descriptions of galaxies as we understand them, they carried a faint premonition that the sky's calm might be an illusion, that somewhere beyond the familiar stars titanic events could unfold on timescales no human eye could follow, a suspicion that would have to wait 2 millennia for technology to catch up before it could be given a scientific form. At the beginning of the 17th century, when Galileo lifted his small, clumsy telescope toward the band of the Milky Way and discovered that its continuous glow broke into innumerable points too small for the naked eye, he took the first hesitant step toward the modern galaxy. He saw that the Milky Cloud was in fact a city of stars, and although he did not yet think in terms of an entire stellar system spinning in space, he had cracked the shell of uniform light and revealed the granularity within. Over the following decades and centuries, as telescopes grew longer and mirrors more polished, astronomers like Christian Huygens, Edmund Halley, and eventually William Herschel began to catalogue faint fuzzy patches in the sky that were not stars at all but smears of dim light, some of them resolving with effort into clusters and some stubbornly remaining misty, leading to the ambiguous label nebulae, clouds whose true nature remained stubbornly opaque. William Herschel and his sister Caroline swept the heavens tirelessly, recording hundreds of nebulae and mapping the distribution of stars in the Milky Way in an attempt to determine the structure of the system in which the Sun resided. And Herschel imagined at first that he might be charting the entire universe. He saw our star system as a vast disk thickened at the centre, and supposed that the faintest nebulae might be distant systems of the same kind, island universes beyond our own, an idea later elaborated by Immanuel Kant, sitting at his desk in Königsberg and thinking about rotating clouds of stars too distant to resolve. But this remained a philosophical speculation, a possibility among many, because without a way to measure their distances, those blurred patches could be either small clouds close at hand or colossal assemblies very far away, and the instruments of the time could not decide between the options. In the 18th century, Charles Messier, hunting comets in the Parisian sky, compiled his now famous catalogue of objects that might be mistaken for comets, but were in fact stubbornly fixed fuzzies, and among these catalogue entries, M31 for Andromeda, M51 for what would later be called the Whirlpool Galaxy, lay the first clues that something more than static clouds hung in the darkness, when, in the mid-19th century, William Parsons, the 3rd Earl of Rosse, turned his gigantic 72-inch Leviathan of Parsonstown toward M51, he sketched a whirling spiral form that startled the astronomical world. Here was a luminous whirlpool, clearly structured, its arms coiling gracefully around a bright nucleus, and in his drawings of other spirals, some of them with smaller companions nearby, there was a hint, not yet recognized, that galaxies did not live in splendid isolation, but sometimes appeared in suspiciously close pairs. Even then, when the first spiral outlines were being inked into observatory notebooks, the thought that such systems might collide with one another hovered just beyond the threshold of plausibility, because 19th century astronomy lived under the sign of stability and harmony, guided by Newton's celestial mechanics, which had so elegantly explained the orbits of planets and comets within the solar system that many came to see the entire universe as a grand extension of this clockwork. If the stars were fixed in their relative positions, and if the faint spiral nebulae were simply smaller arrangements embedded in a larger stellar fog, then there seemed no place for wild, disruptive events on cosmic scales, and the idea that one whirlpool of stars might plunge into another remained foreign, an unimagined possibility. As the 19th century turned into the 20th, and photography began to supplement the eye at the eyepiece, the picture sharpened. Long exposures on glass plates revealed spiral arms in greater detail and showed that some nebulae had strangely distorted shapes. Rings, tails, bridges, though their meaning was still obscure. At the same time, spectroscopy, newly refined, allowed astronomers to split the light from these nebulae into its constituent colours, yielding emission and absorption lines that could be measured and compared so that velocities along the line of sight could be extracted from tiny shifts. And Vesto Slipher at Lowell Observatory started pointing his spectrograph at the spiral nebulae and finding, to his quiet astonishment, that many of them were racing away from the Earth at incredible speeds, hundreds or even over 1,000 kilometers per second, a fact that would later feed into the discovery of cosmic expansion. But that also hinted that these whirlpools were not tranquil decorative patterns on a celestial dome, but independent objects moving rapidly through space. Yet at this point their scale was still unknown, and the astronomical community entered what would later be memorialized as the Great Debate of 1920 between Harlow Shapley and Heber Curtis, an argument staged at the Smithsonian in Washington, D.C., where the question was simple but profound. Were the spiral nebulae part of the Milky Way, floating somewhere within our own star system, or were they separate, enormous stellar systems, island universes, as Kant and Herschel had guessed, lying far beyond our own? Curtis argued for the latter, pointing to novae in Andromeda that seemed too faint and too frequent to be local, while Shapley, who had used globular clusters to map a large sun-descended Milky Way, believed that our galaxy was so vast that it could contain the spirals within it, and he noted that some observers, such as Adriaan van Maanen's reported measurements taken seriously at the time, suggested that the spirals rotated fast enough that, if placed far beyond the Milky Way, their outer edges would have to move faster than the speed of light, which seemed absurd, and so these incorrect observations lent support to the spirals or local side of the debate. The resolution would have to wait a few years until a quiet, meticulous observer at Mount Wilson, Edwin Hubble, exploited a trick discovered by Henrietta Swan Leavitt, who had shown that a special kind of pulsating star, Cepheid variables, had a tight relationship between their period of brightness variation and their intrinsic luminosity, giving astronomers a standard candle to estimate distances. Hubble photographed stars in Andromeda and other spirals, identified Cepheids, and calculated that they lay far beyond the dimensions of the Milky Way, forcing the astronomical community to accept that these nebulae were in fact separate galaxies, enormous star systems like ours, scattered through intergalactic space. Once that mental leap had been made, a quiet shock followed, because the familiar sky, with its constellations and Milky Way band, became just the interior view from within one galaxy among uncounted others, and the faint smudges on photographic plates resolved themselves in the imagination into rotating cities of stars separated by millions of light years. Naturally, the question of how these vast, self-contained systems might interact arose, and some astronomers began to scrutinize the more oddly shaped galaxies, the ones with irregular outlines, curved plumes, or close neighbours, suspecting that gravity might be at work on a grand scale. Fritz Zwicky, that irascible, sharp-eyed Swiss astronomer at Caltech, was among the first to seriously consider the idea that galaxies might collide and merge, though his broader reputation for outlandish ideas caused many of his suggestions, including the reality of dark matter, to be treated with caution if not outright skepticism. Meanwhile, photographic surveys permitted the cataloguing of peculiar galaxies, systems that did not fit neatly into the emerging Hubble classification of ellipticals and spirals and lenticulars, and in 1966, Holt and Arp published his Atlas of Peculiar Galaxies, a richly illustrated compendium of interacting, distorted, ring-shaped, and otherwise extraordinary systems that became a touchstone for studies of galactic encounters. In those pages, one could linger over the twin streams of the antennae galaxies, NGC 4038 and 4039, their long curving tidal tails stretching out like insect feelers, or the slender, drawn-out bodies of the mice galaxies, NGC 4676, sliding past each other with trails streaming behind them, or the crab-like extensions of Stephan's Quintet, a compact group where several galaxies appeared tangled together in a small patch of sky. And even if the word collision still conjured for many an image of stars smashing head-on, astronomers who studied Arp's plates understood that gravitational interactions could distort galactic disks without requiring direct star-to-star impact. The mental hurdle was the scale. Stars within galaxies are so far apart relative to their sizes that even when two galaxies pass directly through each other, the probability that any two individual stars will collide is minuscule, like firing two rifle shots across the width of a football stadium and expecting the bullets to hit. But gravity operates collectively, so the overall gravitational fields of the galaxies feel each other and tug on the orbits of billions of stars at once. This gives rise to what are called tidal forces, differences in gravitational pull across the extent of each galaxy, stretching and compressing the stellar disks and flinging out long arcs of material where stars and gas that once belonged to orderly spiral patterns are drawn into extended tails and bridges. And it was precisely these delicate structures that begged for an explanation as the mid-20th century approached. The breakthrough came in the early 1970s with the work of Alar Toumre and his brother Jury, who used numerical simulations to show that the strange shapes catalogued by Arp could arise naturally from gravitational interactions between galaxies. At a time when computers were still slow and memory expensive, they adopted a clever simplification called the restricted three-body approximation, treating each galaxy as a point mass for the overall gravitational field while populating disks with massless test particles representing stars, and by adjusting orbital parameters, impact angle, relative velocity, mass ratio, they discovered that they could reproduce tidal tails, plumes and bridges almost eerily similar to those seen in photographs, particularly in the case of the antennae and the mice. For the first time, the script of galactic collisions was rewritten from speculative suspicion to dynamical demonstration. These interactions weren't mere accidents but routine outcomes of gravity acting over cosmic timescales. In Toumre's simulations, you can imagine the scene unfolding in accelerated time. Two spiral disks approaching one another, tilting as they come in under the influence of mutual gravity, their outer regions beginning to respond before their centers do, so that stars at the leading edges are tugged forward and outward, forming faint streamers, while the inner regions curve into elongated bars. As the galaxies pass through each other, their dark matter halos interpenetrating, their disks overlapping like ghosts. The tidal forces grow strongest, slinging material out along narrow directions determined by the geometry of the orbit. And over the next few 100 million years, these tails lengthen and thin, while the cores of the galaxies, having lost orbital energy to the surrounding sea of stars via a process called dynamical friction, begin to spiral inward toward a final coalescence. Dynamical friction is a subtle but essential actor in this drama. When a massive body, such as the centre of a galaxy, moves through a sea of stars or dark matter particles, its gravity focuses the orbits of those smaller masses, creating a wake of slightly overdense material behind it. This overdensity tugs backward on the massive body, robbing it of kinetic energy and angular momentum, slowly decelerating its motion relative to the background, and causing its orbit to decay. And in the context of colliding galaxies, this means that the two cores, initially rushing past each other on wide, elongated orbits, gradually sink toward one another, orbit after orbit, until they finally merge into a single, deeper potential well, enclosing a new merged galaxy that often bears little resemblance to the graceful spirals that began the encounter. While the stars largely pass by without direct collisions, the interstellar gas within galaxies is far less forgiving. Hydrogen clouds and molecular complexes, spread throughout the disks, feel pressure and shocks as they overlap, and when the gas from one galaxy slams into the gas from another, it compresses and heats, losing orbital energy much more efficiently than stars can. These compressed regions can collapse gravitationally to form intense knots of star formation, superstar clusters and sprawling starburst regions where new stars ignite at rates tens or even hundreds of times higher than in a quiescent spiral galaxy, driving outflows and winds that can blow gas away from the central regions. This connection between galaxy interactions and starbursts was first teased out in the 1970s and 1980s as infrared telescopes detected luminous, dust-enshrouded galaxies whose energy output, hidden at optical wavelengths, betrayed furious ongoing star formation, many of them residing in obviously disturbed interacting systems. One of the ironies of galaxy collisions is that from a bird's-eye perspective, their motions may be almost balletic, graceful, slowly curved trajectories traced out over billions of years, while internally, in the dense knots where gas is funneled, life and death proceed at an almost frantic tempo. Massive stars born in the compressed gas live only a few million years before exploding as supernovae, enriching the surrounding medium with heavy elements, generating shockwaves that in turn can trigger new generations of star formation, or conversely, blow apart their natal clouds and quench further birth. As telescopes sensitive to different wavelengths came online, radio arrays mapping cold hydrogen, millimeter observatories tracing carbon monoxide as a proxy for molecular gas, X-ray satellites revealing hot plasma, astronomers could see the multi-layered consequences of galactic interactions, from cold, extended tidal tails rich in neutral gas to hot, X-ray bright halos heated by the combined effects of gravitational shocks and stellar feedback. The central regions of colliding galaxies harbour another critical ingredient: supermassive black holes, the millions to billions of solar mass monsters that lurk at the heart of most, perhaps all, large galaxies. Under normal circumstances, these black holes may be relatively quiet, accreting gas at low rates and producing only a modest active nucleus. But when galaxies collide, gravitational torques can drive gas inward, removing its angular momentum and funneling it toward the central few hundred parsecs, where it can feed the black hole more vigorously. This enhanced accretion can light up the nucleus as a quasar, or a less extreme active galactic nucleus, emitting tremendous amounts of radiation, and sometimes launching jets that punch through the surrounding gas and into intergalactic space. And thus the glow of distant quasars, first catalogued in the 1960s as puzzling radio sources with star-like optical counterparts, is now understood in many cases to be the blazing aftermath or accompaniment of galactic mergers early in the universe. When two galaxies, each hosting a central supermassive black hole, merge, their black holes are carried along in the dynamical flow of stars and gas, sinking toward the common centre via dynamical friction. At tens of parsecs separation, the black holes form a bound binary system orbiting one another within a dense stellar environment that can, in principle, continue to drain their orbital energy through gravitational slingshots. Stars passing close to the binary can be ejected at high speeds, carrying away energy and angular momentum, allowing the black holes to spiral closer. At separations of a fraction of a parsec, general relativity takes charge, and gravitational wave emission becomes the dominant means by which the binary loses energy, eventually leading to a final spiral and merger that releases stupendous amounts of energy in the form of ripples in spacetime, waves that propagate out across the universe and, if strong enough and of appropriate frequency, could be detected by gravitational wave observatories sensitive to those low-frequency bands. Although the ground-based detectors LIGO and Virgo are tuned to stellar mass black hole mergers, the merging of supermassive black holes in the hearts of post-collision galaxies leaves its own signature in a different frequency range, one that pulsar timing arrays scattered around the globe are now beginning to probe. By monitoring the ticks of millisecond pulsars, the regular radio beacons of rapidly rotating neutron stars, with exquisite precision, astronomers can search for correlated deviations caused by passing long-wavelength gravitational waves, and recent results have hinted at a background consistent with the combined signal of many supermassive black hole binaries, an ensemble murmur echoing the invisible collisions of galaxy centers over cosmic time, tying the fates of stars and galaxies to the undulations of space-time itself. But long before we could listen for such waves, we had to learn to see the more visible aftermaths of galaxy interactions, and in this respect, a few specific systems have played starring roles in the growing understanding of cosmic collisions. The Antennae galaxies, located some 60 million light-years away in the constellation Corvus, became a textbook example. Long exposure images show two bright knotted cores embedded in extended, twisted disks lit with pinkish patches of hydrogen emission, indicating active star formation, and two striking tidal tails arc outward in opposite directions, dotted with blue star clusters. Multi-wavelength observations have revealed that the central overlap region between the original disks is a tumult of compressed gas, shock fronts, and starburst activity, with hundreds of massive star clusters forming in relatively tight proximity, some of which may evolve into globular clusters orbiting the final merged remnant. Likewise, the mice galaxies in Coma Berenices, with their slender, luminous tails trailing off like streaks of light behind the main bodies, illustrate a different stage and geometry of collision. Rather than having already merged cores, these galaxies are observed near their first close passage, caught in the act of mutual tugging and stretching, an early frame in a movie that simulations can extrapolate forward, predicting how many more orbits will pass before they coalesce. Similarly, the Cartwheel Galaxy, a remarkable ring-shaped system located about 500 million light-years away, presents the aftermath of a smaller galaxy, plunging almost head-on through the disk of a larger one, producing a radially propagating wave of compression in the disk, like the circular ripples spreading outward after a stone is thrown into a pond, that ignites star formation in a bright ring, leaving behind a complex network of spokes and knots visible in optical and X-ray light. Even more dramatic in a different way is Stephan's Quintet, a compact grouping in Pegasus where several galaxies appear closely packed, one of them in fact lying in the foreground and not truly part of the physical cluster, while the others are engaged in a complex gravitational interplay. The intruder galaxy NGC 73 Chimol 8b, plunging through the group's intergalactic medium at high speed, drives a massive shock front that glows brightly in X-rays and emits copious radiation in the infrared, a vast intergalactic scale collision between gas clouds rather than stars, revealing that galaxy interactions are often embedded in richer environments, where group or cluster gas mediates and enhances the violence of encounters. As radio telescopes map neutral hydrogen in these systems, they find vast reservoirs swept into bridges and tails extending far beyond the optical light, tracing the diffusion of baryonic matter into the intergalactic medium through the agency of tidal forces and ram pressure. Galaxy collisions do not occur in a uniform, featureless universe, but within the cosmic web of large-scale structure, filaments, walls, and voids that emerge from the initial density fluctuations seeded in the early universe. In the prevailing LCDM, lambda-cold dark matter cosmological model, small dark matter halos collapse first, drawing in gas and forming the first dwarf galaxies, and over time these halos merge hierarchically, forming progressively larger structures, groups, clusters, massive galaxies, so that mergers are not occasional anomalies but the main arteries of galactic growth. Simulations of structure formation, such as the Millennium simulation, and later hydrodynamical runs like Illustris, Eagle, and TNG, have shown how countless minor and major mergers build up the halos of present-day galaxies, and observational evidence in the form of stellar streams and shells in the outskirts of galaxies supports this picture. These faint arcs are the shredded remains of smaller companions swallowed in the past, fossil scars of long-completed collisions. Within galaxy clusters, where hundreds or thousands of galaxies move through a common gravitational well, the collision story acquires additional characters. The hot X-ray emitting intracluster gas through which galaxies plough, and the cluster's massive dark matter halo, which shapes the overall potential. In these crowded environments, high-speed encounters between galaxies can truncate disks and strip gas, a process sometimes called galaxy harassment, altering their morphologies without necessarily leading to full mergers, because the relative velocities are often so high that galaxies simply fly past each other after a brief, bruising interaction. Nonetheless, in centers of clusters where velocities can be moderated by the deep potential and where galaxies accumulate, massive central cluster galaxies called CD galaxies may grow by cannibalizing smaller satellites, their envelopes swelling with the addition of stars from unlucky neighbors that wander too close and are gradually shredded by tidal forces, their remnants joining the diffuse intracluster light. One of the most striking confirmations that collisions between large dark matter-dominated structures can be probed directly came with the observation of the Bullet Cluster, a system of two colliding galaxy clusters located about 3.8 billion light-years away. X-ray telescopes like Chandra reveal a bullet-shaped cloud of hot gas that has been ram pressure stripped from one of the clusters as it ploughed through the other's intracluster medium, while optical images show that the galaxies themselves have mostly passed through each other without major disruption. Weak gravitational lensing maps of the mass distribution, however, indicate that the bulk of the mass is not associated with the shocked gas, but with the galaxies, suggesting that an unseen dark matter component has behaved collisionlessly, passing through the collision largely unaffected, in stark contrast to the colliding gas. This spatial separation between mass and baryonic plasma provides one of the clearest pieces of evidence for dark matter's physical reality, and illustrates that even on cluster scales, cosmic collisions are multi-component, involving gas, stars, and dark matter, each responding differently to the encounter. If we shift our gaze from clusters back to individual galaxies, we can trace collisions not only in the spectacularly distorted systems, but also in more subtle signatures embedded in seemingly ordinary galaxies. Kinematically decoupled cores in ellipticals, counter-rotating disks of gas and stars, misaligned angular momentum axes, and populations of globular clusters with distinct metallicities and orbital properties, all pointing to multiple assembly episodes. High-resolution simulations have shown that major mergers of spiral galaxies can transform them into pressure-supported stellar systems, resembling ellipticals, their orderly disks scrambled into a more isotropic velocity distribution, while minor mergers, where a small galaxy is accreted by a larger one, tend to puff up disks, thicken stellar components, and deposit streams of stars into the halo, and thus the Hubble sequence of galaxy morphologies can be understood as, in part, a record of their past collisions and interactions. As radio telescopes like the Very Large Array and ALMA map the cold gas content of galaxies across cosmic time, a finer-grained picture of how collisions influence star formation emerges. In some interactions, gas is efficiently driven toward the center, creating compact starbursts and feeding the central black hole, while in others, tidal forces launch gas into extended tails and bridges, where it may form stars in more diffuse, scattered fashion or remain as a reservoir to be later reaccreted. Observational studies of luminous and ultra-luminous infrared galaxies, many of which are merger systems, reveal that star formation efficiencies can be dramatically enhanced compared to isolated galaxies, but only under particular orbital configurations and gas fractions, and that feedback from both supernovae and active nuclei can rapidly shut down the burst, expelling or heating gas and potentially transforming a blue, star-forming merger remnant into a red, quiescent elliptical galaxy over relatively short timescales in cosmic terms. The role of environment and cosmic epoch becomes especially apparent when we peer deep into the universe, looking back in time. Surveys with the Hubble Space Telescope's deep fields show that at redshifts of 1 to 3, corresponding to when the universe was a few billion years old, galaxies were more irregular, clumpier, and more frequently engaged in interactions. Their morphology is less settled into the neatly classified spirals and ellipticals familiar in the local universe, and the global star formation rate density of the cosmos peaked around this period, likely driven in part by the higher rate of mergers and gas accretion. Many of the luminous quasars we see at high redshift, shining with the light of rapidly growing supermassive black holes, inhabit host galaxies that bear signs of recent or ongoing mergers, though not exclusively, hinting that while collisions are an efficient way to funnel gas into galactic centres, they are not the only path to fueling active nuclei. Historically, as astronomers absorbed this view of a dynamic universe in which galaxies collide, merge and transform, there was an echo of earlier scientific revolutions. Just as geology in the 19th century shifted from a static Earth to one shaped by deep time and catastrophic events like volcanic eruptions and asteroid impacts, cosmology in the 20th century moved from a picture of fixed stars on an eternal firmament to one of evolving structures, where collisions between galaxies play the role of mountain building and erosion on grander scales. The initial resistance to such a violent universe softened as more observational evidence accumulated, and by the latter half of the 20th century the idea that galaxy encounters are common had seeped into textbooks and popular accounts, images of the antennae and other mergers gracing posters and planetarium shows, turning the once abstract notion of island universes into something more like crashing continents. The future collision between our own Milky Way and the Andromeda galaxy provided a particularly compelling narrative hook for popular imagination, but its scientific foundation rests on careful astrometric measurements. For a long time, astronomers knew that Andromeda was approaching us at about 110 kilometers per second along our line of sight, thanks to the Doppler shift of its spectral lines. But its motion across the sky, the tangential component, was much harder to measure, requiring the tracking of tiny positional changes over years or decades. With the Hubble Space Telescope, teams led by scientists like Roland van der Machel finally measured Andromeda's proper motion by comparing images taken years apart, using background quasars as fixed reference points, and found that the transverse velocity is small enough that Andromeda is indeed on a largely head-on course toward the Milky Way, setting the stage for a future galactic collision some 4 to 5 billion years from now. Simulations tailored to the measured masses, dark matter halos, and relative velocities of the Milky Way and Andromeda, sometimes including the effects of our smaller neighbour, the Triangulum galaxy, predict the broad outlines of what will happen. As Andromeda's enormous halo of dark matter and tenuous gas begins to overlap with our own, subtle tidal effects will first warp the outer regions of each galaxy. Over a few billion years, the two disks will interpenetrate, likely triggering episodes of enhanced star formation as gas is compressed, though the relatively modest gas fractions of both galaxies by that time may limit the intensity of the starburst compared to those seen in gas-rich, high redshift mergers. In the night sky, for any hypothetical observers clinging to planets that survive the sun's own evolving luminosity, Andromeda would grow from a faint smudge to a vast, distorted arc, eventually spanning a dramatic fraction of the sky as the two stellar systems weave around each other in slow, majestic loops. Contrary to some dramatic illustrations, the collision is unlikely to pose a direct threat to the solar system via stellar impacts because of the immense distances between stars. The Sun and its planets will almost certainly glide through the encounter without another star passing close enough to gravitationally unbind the planets, though there is a non-zero probability of distant perturbations to the outer Oort cloud or to the orbits of more loosely bound objects. More consequential may be the long-term gravitational influence of the merged galaxy's mass distribution and any changes in the Sun's orbit around the centre, which could migrate inward or outward over billions of years, altering the galactic environment in which the solar system finds itself. But on human timescales, these changes are essentially imperceptible, and by the time the final coalescence into a single, more spheroidal galaxy, sometimes dubbed Milkomeda in informal context, occurs, the Sun itself will be nearing the end of its hydrogen-burning life, swelling toward the red giant phase. from the vantage point of a far future civilization orbiting some other star within the merged remnant, the sky would tell a different story. Rather than the thin wheeling band of a spiral disk, they might see a more rounded, diffuse glow of stars extending in all directions, punctuated perhaps by the faint, ghostly arcs of tidal streams from smaller galaxies still falling in. And the record of the Milky Way Andromeda collision would be written not as a sudden catastrophe, but as a slow resculpting of the gravitational landscape, a process that, for all its violence in simulations, unfolds so gradually that no single lifetime can span its beginning and end. Yet even without seeing the entire drama, that civilization, armed with telescopes and the accumulated wisdom of astrophysics, could read their galaxy's history in the motions and ages of its stars, in the structure of its halos, in the chemical fingerprints of its gas, and reconstruct the collision that gave birth to their home. On smaller scales and shorter times, collisions continue to shape galaxies across the universe right now. In nearby groups, faint dwarf galaxies are being tidally shredded by more massive neighbours, leaving behind stellar streams that arc through halos like ghostly rivers. The Sagittarius dwarf spheroidal galaxy, for instance, has been falling into the Milky Way for billions of years, its stars stretched into a looping stream that wraps around the sky. Discovered in the 1990s and mapped in detail by surveys like the Sloan Digital Sky Survey, and more recently by the Gaia mission, whose precise astrometry has revealed a host of kinematic substructures in the Milky Way's halo, evidence for multiple past mergers, such as the Gaia-Enceladus-Chiak sausage event, a significant collision roughly 8–10 billion years ago that deposited a swarm of stars on highly radial orbits and likely contributed substantially to the inner halo's mass. These stellar archaeological clues demonstrate that even galaxies that look relatively undisturbed today have lived turbulent pasts, and that collisions come in many flavours: dramatic major mergers between roughly equal mass spirals, gentler minor mergers with dwarfs, repeated high-speed encounters and clusters, and slow accretion of gas from cosmic filaments that can, over time, feed disks and build up mass without discrete, easily identifiable collisions. Yet across this spectrum, the underlying physical principles remain grounded in gravity, orbital dynamics, and the complex dissipative behaviour of gas, all of which combine to produce the rich variety of structures we observe, from grand design spirals with two elegantly symmetric arms, to flocculent spirals with chaotic patchy patterns, to smooth ellipticals and lenticular galaxies, with their subdued disks and older stellar populations. The theoretical tools used to study these processes have grown more sophisticated over time, moving from the idealized test particle simulations of Tumri to full n-body codes that compute the mutual gravitational interactions of millions or even billions of particles representing stars and dark matter, coupled with hydrodynamical solvers that track the behavior of gas, its cooling, heating, star formation, and feedback. Codes like Gadget, Arepo, and Ramses have been used to perform controlled simulations of specific galaxy collisions, matching initial conditions to observed systems in order to reproduce their present-day morphologies and infer their past orbital histories, as well as large cosmological runs that generate populations of galaxies whose statistical properties can be compared to real surveys, giving insight into how typical or unusual specific collision scenarios might be. In these detailed simulations, one can watch the interplay between dark matter halos, massive, extended, roughly spherical structures that envelop galaxies and dominate their gravitational potential, and the more concentrated baryonic components of stars and gas. When two halos merge, they can absorb galaxies like droplets within larger drops, their dark matter mixing and relaxing into a new equilibrium, while the luminous components may experience sharper shocks, forming new disks or spheroids depending on the angular momentum and energy budgets. Tidal stripping during these mergers can peel away both dark and luminous matter, seeding the environment with substructure and providing a reservoir of material that may eventually accrete onto other systems, contributing to the intricate choreography of matter within the cosmic web. Beyond the purely scientific fascination, the recognition that galaxies collide has had a subtle cultural impact. It has altered the way we visualize the universe and our place within it, transforming the night sky from a static backdrop into a dynamic arena where slow-motion cataclysms unfold in silence, far beyond any human ear's capacity to register. Artists, filmmakers and writers have borrowed imagery from Hubble's portraits of colliding galaxies, turning them into emblems of both destruction and creation, cosmic analogues of forest fires that clear the way for new growth, of tectonic collisions that raise mountain ranges, of the chaotic interactions that may, in the end, be necessary to produce the rich diversity of galactic forms and environments that can, in some corners, give rise to planets, life, and eventually minds capable of pondering the very collisions that set their stage. This cultural assimilation carries an echo of earlier shifts in cosmic perspective. When Copernicus moved the Earth from the centre of the universe to a planet circling the Sun, and when Hubble and others showed that the Milky Way was just one galaxy among countless others, humanity was forced to adjust its sense of significance. The realization that entire galaxies can merge and reshape themselves over billions of years adds another layer to this ongoing recalibration, reminding us that even the structures we once considered almost unimaginably vast and stable are themselves transient patterns in an evolving universe, subject to encounters and transformations that, while far beyond the timescale of human civilizations, are nonetheless part of the same physical laws that govern a falling apple or the orbit of a satellite around Earth. As we continue to build ever more capable observatories, radio arrays like the Square Kilometre Array, optical and infrared surveys like the Vera-C, Rubin Observatory's legacy survey of space and time, space telescopes like the James Webb Space Telescope and its successors, we will collect deeper and more detailed observations of galaxies at all stages of collision, from the first subtle tidal distortions in otherwise normal disks to the final relaxation of merger remnants and the settling of their new morphologies. JWST, with its infrared sensitivity, is already peering through dust in the central regions of interacting galaxies, resolving star-forming clusters and gas flows that were previously hidden, while integral field spectrographs on large ground-based telescopes map the kinematics of stars and gas across collisional systems, revealing complex velocity fields that betray past encounters. Simultaneously, refinements in numerical modelling and increased computing power will allow simulations to incorporate more realistic physics, magnetic fields, cosmic rays, radiative transfer, capturing the full richness of processes at play in galaxy collisions and making more precise predictions that can be tested against observations. Experiments in laboratory astrophysics, using powerful lasers and plasma devices, even attempt to recreate some of the microphysical conditions relevant to interstellar shocks and instabilities, bridging scales from the subatomic to the cosmological, all in service of understanding how the vast, slow dance of galaxies translates into the more immediate turbulent environments where stars are born. In that sense, following the trail of what happens when galaxies collide leads us from the human eye gazing at a hazy smudge in Andromeda, to carefully calibrated instruments that can dissect the light from distant mergers into detailed spectra, from mythic imaginings of sky gods in conflict to rigorous simulations of dark matter, halos interpenetrating, from philosophical notions of eternal unchanging heavens to a universe whose very large-scale structure is sculpted by repeated, sometimes violent encounters. And although each individual collision unfolds too slowly for any one observer to witness in full, by stitching together snapshots at different stages, both in space and in time, across the observable universe, we can reconstruct the storylines of countless galactic lives, seeing in their past and future collisions not random catastrophes, but integral steps in the grand, ongoing evolution of cosmic structure. To probe more finely what unfolds inside these vast encounters, astronomers began to read galaxies almost the way a geologist reads a mountain range, not as a single monument, but as the superposition of many past events. And in this forensic work, the subtlest details, faint ripples of starlight on the outskirts of an otherwise smooth elliptical, odd kinks in a disk's rotation curve, abrupt changes in stellar age with radius, became clues to collisions that ended long before Earth formed. When powerful telescopes started pushing deeper in surface brightness, especially with careful image processing designed to bring out the dimmest structures, objects once written off as featureless spheroids suddenly revealed arcs, shells, and umbrellas of light. Patterns that theoretical work showed could result when a smaller galaxy plunges through a larger one, its stars flung onto elongated orbits that phase wrap over time, piling up at the apocenters of their paths and sketching luminous caustics in the halo. The French astronomer François Schweizer, among others, catalogued such shell galaxies in the late 20th century, noting that many resided in environments rich with potential victims, loitering dwarfs and modest companions whose slow demise could feed the growth of the host. Careful modelling indicated that when a disk galaxy is swallowed by a more massive elliptical or a zero, the incoming stars, particularly those from the outer regions, can preserve a memory of their original orbital energy and angular momentum manifesting as a series of nested concentric shells whose brightness gradually fades as dynamical mixing proceeds, and in some spectacular cases, like NGC 3923, dozens of such structures can be traced, each one a fossilized wavefront from an ancient collision, frozen in the projection we see from Earth. Another odd class, polar ring galaxies, offered a different window into off-axis encounters. Here, a central spheroidal or lenticular system is girdled by a nearly perpendicular ring of gas and stars orbiting in a plane at right angles to the main body's rotation. Objects like NGC 4650A puzzled observers until simulations showed that such configurations can emerge when a gas-rich dwarf or low-mass disk is disrupted on a polar trajectory, depositing its material into a stable, high angular momentum orbit around the more massive host. The resulting ring, while delicate in appearance, can persist for billions of years, and because its orbital plane samples the host's gravitational potential in a direction distinct from that of the central stellar body, astronomers can use its kinematics to constrain the shape of the surrounding dark matter halo, turning a rare byproduct of a long-ago collision into a diagnostic tool for the invisible. If you shift focus from the shapes to the motions within colliding systems, a different level of structure reveals itself, one that depends on the marriage of spectroscopy and spatially resolved imaging. With integral field units, optical instruments that break up the light from each small patch of a galaxy into a spectrum. Astronomers can now build detailed two-dimensional maps of velocity, tracing how gas and stars move not just along a single slit, but across the whole object. In interacting pairs like NGC 6240 or the Taffy galaxies, these kinematic maps show counter-rotating streams, shock fronts where gas from one disk slams into that of the other, and regions where rotation has been disrupted into complex vortices, patterns that can be fed back into dynamical models to refine our understanding of the orbits that led to the present tangle. Inside those turbulent knots, the conditions for star formation diverge markedly from those in calm spiral arms. Instead of relatively gentle density waves quietly gathering gas into clouds, collisions can generate supersonic turbulence, high pressures, and strong tidal fields that both tear structures apart and, paradoxically, create compressive tides in certain regions, where the combined gravitational pull of the interacting galaxies squeezes gas rather than stretching it. Numerical experiments that track individual giant molecular clouds, the cold, dense nurseries of stars, show that in these compressive zones, clouds can survive disruptive feedback for longer and reach higher densities, leading to the formation of particularly massive and bound stellar. The physical thresholds for this explosive mode of star formation can be expressed in quantitative terms. The famous Toomri Q parameter, originally devised to assess the stability of rotating disks against gravitational fragmentation, becomes a useful guide with values dipping below unity, indicating that gas in a local patch is prone to collapse. During an encounter, gravitational torques, shocks, and inflows can drive Q downward in selected zones, while elsewhere, strong tidal forces and heating raise it above the threshold, quenching collapse. Thus, a single collision can carve a patchwork of intensely active and thoroughly suppressed regions across both galaxies, creating radially inverted star formation profiles, nuclear bursts surrounded by relatively quiescent rings. or in some cases widespread but clumpy activity dispersed across tidal features. On larger scales, collisions act as mixers of galactic chemistry, scrambling the gradients that otherwise build up slowly over time as repeated generations of stars enrich their surroundings. In a normal disk, heavy elements, the metals in astronomical parlance, tend to be more concentrated near the centre, where star formation has proceeded longest and gas densities are higher, producing a fairly smooth decline in metallicity with radius. But when another galaxy plunges in, gas from the outskirts can be funneled inward, while enriched inner gas is tossed outward in tails and plumes. Spectroscopic surveys of interacting pairs show flatter metallicity gradients than in isolated systems, sometimes with distinct pockets of high or low metallicity associated with inflows or out, while the grand two-body collisions between roughly equal partners tend to draw the most attention. The universe is equally busy staging more lopsided encounters, where a small galaxy is captured by a larger one and incrementally digested, a process that can be repeated dozens of times throughout a massive galaxy's life. These minor mergers may not produce cinematic tidal tales, but they leave quieter marks. Warps in outer disks, flares in stellar thickness, subtle kinematic components whose orbits are angled relative to the main rotation, and low surface brightness streams that can only be seen with painstaking exposures. In the outskirts of massive spirals, careful studies have uncovered dwarf galaxies in the very act of being torn apart, their stars splayed along arsing tracks that connect luminous knots, the surviving cores to diffuse fans of light, and in some cases, such as the disruption of the Canis Major and Sagittarius dwarfs in the Milky Way's halo, these ongoing accretion events can be followed almost in real time as Gaia refines the orbits and membership of their dispersed stars. The gravitational influence of a substantial satellite can affect not just the halo, but the central disk structure. The Large Magellanic Cloud, for instance, is massive enough that its orbit around the Milky Way, coupled with its gravitational tug, is now thought to contribute to the warp of our galaxy's outer gas disk and to subtle asymmetries in the rotation curve. High-resolution simulations in which a Milky Way-like galaxy is bombarded by satellites of various masses and trajectories show that repeated minor impacts can heat the disk, turning a once thin plane into a thicker layered configuration, and can stimulate the formation of bars and spiral patterns. Thus, even collisions that are far from head-on and that never approach the destructive intimacy of a major merger can nonetheless reshape a galaxy's visible architecture, spurring secular evolution that might otherwise take far longer. On the other end of the mass spectrum, collisions between dwarfs, systems with only a few billion stars or less, compose their own, understudied chapter of this story. Because dwarfs often inhabit the same filaments and groups as their larger cousins, they can pair up, merge, and pass through one another in environments where the external tidal field is relatively mild, allowing fragile structures to persist. Some blue compact dwarf galaxies, with their concentrated bursts of young, massive stars, have been interpreted as the result of dwarf-dwarf mergers that trigger centralized gas inflows, while elongated, irregular shapes in other dwarves betray past harassment. Intriguingly, tidal tails thrown out during such encounters can, in certain conditions, form self-gravitating condensations of gas and stars that coalesce into what are called tidal dwarf galaxies, secondary systems born not from the collapse of their own dark matter halos but from the recycled material of larger progenitors, and their unusually low dark matter content provides an observational handle on how such structures differ from classical dwarves. To chart how common any of these scenarios are across cosmic epochs, astronomers turn to statistics, scouring large surveys not just for eye-catching showpieces, but for all close pairs and morphologically disturbed systems. Criteria had to be devised. How close is close enough in projection to plausibly represent an imminent or ongoing merger? What range of velocity differences indicates bound pairs versus mere chance alignments? What quantitative measures of shape, concentration, asymmetry, clumpiness, Gini coefficient, M20 moment of light, best distinguish interacting from isolated galaxies? Automated algorithms, supplemented by human classification efforts like the Galaxy Zoo Citizen Science Project, sifted millions of images, flagging lopsided double nucleus or tail-bearing systems, and by comparing the fraction of such objects as a function of redshift, astronomers inferred how the merger rate evolves, generally finding that encounters were more frequent when the universe was younger, in line with the hierarchical growth paradigm. These morphological methods have their biases. Tidal features can be short-lived, fading below detectability within a few 100 million years, and gas-pore mergers between ellipticals, so-called dry mergers, can leave relatively subtle signatures, particularly in optical imaging. To complement shape-based approaches, closed pair counts focus on systems whose projected separation and redshift similarity imply a likely future coalescence within a specified timescale, providing a somewhat different window on upcoming collisions. The combination of both techniques, cross-checked with mock observations of simulated universes where the true merger histories are known, has gradually tightened estimates of how many major and minor mergers a typical massive galaxy has experienced since Redshift 2, painting a picture in which quiet, solitary evolution is the exception rather than the rule. Collisions, however, do not act in isolation as the sole sculptors of galactic form. Secular processes, internal instabilities that develop over long timescales within a relatively undisturbed disk, can also build bars, rings and pseudobulges, and one of the challenges in interpreting any given galaxy structure lies in disentangling which features were primarily shaped by interactions, and which by slow internal reconfiguration. Bars, for instance, can be induced or strengthened by a flyby that perturbs the disk's angular momentum distribution, but they can also grow purely from the self-gravity of the disk in isolation, redistributing angular momentum as they transfer gas inward and stars outward. Similarly, central bulge-like components can form when repeated minor mergers deposit stars into the central regions, but they can also emerge from the vertical buckling of bars or from sustained gas inflow feeding central star formation. In many galaxies, evidence points to a hybrid history where both collisional and secular effects have contributed, their relative weights varying with cosmic time and environment. The question of how collisions influence the growth of central supermassive black holes intersects with these structural considerations. Empirical correlations like the famous relationship between black hole mass and the velocity dispersion of the surrounding bulge, the M-sigma relation, suggest a deep connection between the buildup of central stellar mass and black hole accretion, and one widely explored hypothesis is that major mergers are particularly efficient at driving gas toward the very center, simultaneously building bulges and feeding black holes. Hydrodynamical simulations of merging disks with embedded black holes show that gravitational torques can indeed strip angular momentum from gas on kiloparsec scales, dumping it into a compact circumnuclear disk from which further processes, viscous torques, gravitational instabilities, magnetic stresses, can deliver material across the last parsecs. Once the black hole ignites, the resulting radiation and mechanical outflows can, in turn, expel gas from the central regions or heat it enough to prevent further inflow, imprinting a feedback loop that may help set the observed scaling laws. Observationally, the link between mergers and luminous active nuclei appears strongest at the high luminosity end. Many of the brightest quasars, especially at intermediate redshifts, inhabit host galaxies that show clear signs of recent interactions. Distorted morphologies, close companions, double cores, supporting the idea that galaxy-scale collisions play a crucial role in triggering the most extreme accretion episodes. At lower luminosities, however, a significant fraction of active galactic nuclei are found in systems without obvious tidal signatures, implying that more modest fueling can be accomplished by internal disk processes, minor companions, or smooth cosmological inflows. This nuanced picture underscores that while collisions are not the only route to feeding a black hole, they are among the most dramatic and may dominate at particular epochs, especially in the dense, rapidly evolving environments of young galaxy groups and protoclusters, as theorists refined models of black hole coalescence at the hearts of merged galaxies. The prospect of detecting their gravitational waves in the relatively near future gained substance. Space-based interferometers like the planned LISA mission are designed to be sensitive to the millihertz frequency band, where the spirals of black holes with masses between 100,000 and 10 million suns will signal their final orbits. Simulations of galaxy assembly predict a rich population of such events, especially during the peak periods of merger activity in the early universe, and by combining merger trees from cosmological models with prescriptions for black hole seeding and growth, researchers estimate event rates and characteristic strain distributions redshift by redshift. If and when such signals are measured, They will not only confirm in exquisite detail the relativistic dynamics of coalescing black holes, but also serve as a new kind of tracer for the otherwise unseen final stages of galaxy collisions. One tantalizing, still debated observational signature of these late stages is the possibility of recoiling black holes kicked out of the very centers of their merged galaxies by the anisotropic emission of gravitational waves during coalescence. General relativistic simulations show that if the spins and masses of the merging pair align in symmetrical arrangements, the newly formed single black hole can receive a substantial velocity boost, in some cases strong enough to displace it by hundreds or even thousands of kilometers per second. In gas-rich environments, such recoiling black holes might carry along a compact accretion disk and a retinue of tightly bound stars, revealing themselves as off-nuclear quasars or as broad emission line sources with velocities offset from their host's rest frame, and a handful of candidate objects have been reported, though alternative explanations, such as unusual disk kinematics or multiple nuclei in ongoing collisions, are often hard to rule out. Beyond their direct astrophysical interest, galaxy collisions have become useful testbeds for theories that attempt to modify gravity instead of invoking dark matter. In such alternative frameworks, the details of how mass distributions respond during interactions, how rotation curves behave in tidal features, and how gravitational lensing maps line up with baryonic traces provide crucial discriminants. Systems like the bullet cluster, where the separation between the dominant mass component and the hot gas is pronounced, and colliding groups where multiple subclusters have passed through one another at high speed, place stringent constraints on how any modified gravity law must behave in the nonlinear regime. Detailed modelling of interacting galaxies under both standard dark matter and altered gravity prescriptions continues, with some proponents highlighting tidal dwarfs or the dynamics of extended tails as potentially supportive of their views, while the bulk of the community finds the concordance of collision-related observables with the LCDM framework persuasive. Alongside these theoretical debates, the observational canvas of galaxy collisions has been steadily enriched by views at wavelengths far beyond the optical, each revealing different facets of the same underlying dynamical events. Ultraviolet imaging, for instance, emphasizes the youngest, hottest stars born in collision-induced episodes, tracing the most recent million years of activity, and highlighting extended structures like tidal bridges, where diffuse blue light betrays star formation in what would otherwise seem empty space. Mid-infrared data from missions like Spitzer and WISE bring out the glow of warm dust heated by young stars and active nuclei, often unveiling obscured central regions where optical light is heavily attenuated. Far-infrared and sub-millimeter observations from instruments such as Herschel and ALMA pick up the emission from the coal dust and dense molecular gas reservoirs that fuel ongoing and future star formation, allowing precise measurements of gas mass and temperature distributions in complex overlapping disks. At radio frequencies, wide-field interferometric arrays map neutral hydrogen, tracing where it has been swept into elongated streams or clumped into fallback structures around the remnants, and detect synchrotron emission from cosmic rays accelerated in shock fronts and supernova remnants, painting collisions as not only gravitational episodes, but also particle accelerators on galactic scales. Polarization studies reveal how magnetic fields are stretched, compressed, and sometimes unraveled during interactions, with field lines draped along tidal tails or amplified in collision zones, potentially influencing how and where gas can fragment. Together, this multi-wavelength view transforms a single merger into a layered phenomenon, with each band highlighting a different age of the event, from long-lived kinematic scars in the stars to the fleeting glow of dust, warmed by newborn star clusters. In parallel with this deep physical exploration, a more speculative line of thought has considered how galactic collisions might affect the broader habitability of galaxies, not in the catastrophist sense of stars slamming into one another, but through their influence on radiation environments, gas content, and orbital stability. In the densest phases of major mergers, the surge in supernova and, in some cases, the ignition of a powerful active nucleus can flood regions with high-energy photons and cosmic rays, which, if intense and long-lasting enough, might erode planetary atmospheres or alter the chemistry of interstellar clouds where new planetary systems are forming. Models of cosmic habitability that attempt to account for factors like metallicity, necessary for rocky planet formation, supernova proximity, and long-term orbital calm, often find that the outskirts of large spirals and the less crowded regions of small groups offer the most benign conditions, while the chaotic cores of merging systems may be less forgiving, at least temporarily. On the other hand, collisions also redistribute metals and dust, enriching regions that might otherwise have remained too primitive in composition to build Earth-like planets, and they can stir gas in ways that reignite star formation in galaxies that had begun to fade. From this angle, encounters act as both hazard and opportunity, complicating any simple equation that would assign a single habitability score to a galaxy. If you imagine a civilization emerging around a star in a galaxy that has just experienced a major merger, its night sky might be brighter, its ambient cosmic ray background higher, its rate of nearby supernova elevated, but it would also inhabit a stellar population with a rich inventory of heavy elements, perhaps increasing the diversity of planetary architectures available, so that even in this astrobiological speculation, the imprint of collisions resists easy moralizing as purely destructive. To appreciate just how varied the choreography of galaxy collisions can be, it helps to follow, in imagination, a canonical major merger from first approach to final relaxation, not at the level of the entire population, but as one specific narrative, reconstructed from simulations and stitched from analogues observed at different points. Far apart in a modest group, two spiral galaxies glide through the common dark matter potential, each surrounded by a cocoon of hot gas and in falling satellites, their disks oriented at arbitrary angles relative to one another. Over billions of years, dynamical friction within the group slowly draws them together as their halos exchange energy with the background population and their orbits decay. On some otherwise unremarkable epoch, the outer reaches of one halo begin to sense the presence of the other, slight asymmetries in the gravitational pull, nudging tracers in the outskirts from their nearly circular paths. As the galaxies approach their first close passage, the relative motion is neither a straight-line crash nor a gentle sidle, but a curved plunge determined by the balance of kinetic and potential energies they carry. At pericenter, their centers may miss each other by several kiloparsecs, yet the tidal force across each disk spikes, pulling leading-edge stars and gas outward and backward, while the trailing edges feel an opposite tug, setting up spiral-like distortions even in systems that were initially only weakly barred. In a few tens of millions of years, an eye blink on cosmic scales, material flung ahead in these tidal arms extends tens of kiloparsecs into intergalactic space, while at the same time, the central regions experience compressive forces that can ignite new rounds of star formation. After this first encounter, the galaxies separate, each trailing tails, their disks now tilted and warped by the impulsive distortion. Yet the energy lost to tidal heating and to the excitation of internal motions ensures that they will not escape one another's grasp. Their paths curve back toward the common centre of mass, describing elongated loops that bring them into a second, often closer embrace, during which the original disks are even more severely damaged. By this point, the orbits of many stars have been heavily randomized, transformed from ordered circular motions into more elliptical three-dimensional trajectories, so that by the time the cores finally coalesce, the emerging remnant may bear little kinematic resemblance to a spiral. Instead of being rotationally supported, with most stars orbiting in the same direction, it can be supported by velocity dispersion, with stars moving on boxy orbits that fill out a spheroidal volume, the birth of an elliptical or lenticular galaxy from the ruins of two rotating disks. After the central merger, the outer debris continues to fall back. Some of the material in the tidal tails is gravitationally unbound and will drift along group potentials or eventually join intragroup light, but much remains loosely attached, tracing elongated orbits that slowly circularize and sink, building extended envelopes and halos over billions of years. The remnant's central black holes, if both progenitors hosted one, spiral toward one another and may merge, as described before, while the stellar body undergoes violent relaxation, a collective redistribution of energies and orbits that tends to smooth out density irregularities, erasing the most obvious substructures and drawing the system toward a new equilibrium. Only the deepest imaging long after will reveal that this smooth elliptical is, in fact, a palimpsest of multiple collisions, each slightly misaligned, each contributing to the final shape and kinematics. In environments with even richer populations, multi-body interactions introduce further complexity. In compact groups, 3 or more galaxies can engage in gravitational tug-of-war, with energy and angular momentum traded among them, so that one object may be flung outward on a higher energy orbit while others sink more rapidly toward coalescence. Simulations of so-called galaxy threshing show how repeated close passes can strip a smaller group member down to its dense central nucleus, leaving behind a compact high surface brightness object orbiting a massive host, an ultra-compact dwarf galaxy that may be the remnant core of a once normal system. Observations in nearby clusters, such as Fornax and Virgo, have uncovered populations of such compact objects, their elevated metallicities and complex stellar populations hinting at a past in which they were more than simple, monolithic star clusters. These diverse fates underscore that collisions are not binary events with a single outcome, but branching processes whose results depend on the initial mass ratios, gas fractions, orbital geometries, and environmental context. A head-on plunge between two extremely gas-rich disks in the early universe might leave behind a hyperluminous infrared galaxy, blazing with obscured star formation, while a slow, glancing impact between gas-poor ellipticals in a present-day cluster core might produce only a modest change in shape and size, thickening envelopes and generating diffuse halos. Intermediate cases abound. S0 galaxies, with their lenticular shapes and quenched star formation, may form when spirals are stripped of gas by interactions and ram pressure, yet retain some disk structure, while compact quenched galaxies at high redshift, the so-called red nuggets, might represent the remnants of early dissipative mergers that built dense stellar cores which later puffed up by accreting smaller companions. As computational cosmology matured, these varied pathways could be followed not just in isolated, idealized simulations, but in fully self-consistent volumes that start from initial conditions seeded soon after the Big Bang. In these virtual universes, governed by the equations of gravity and hydrodynamics, galaxies emerge naturally as gas cools and settles into halos, and their subsequent collisions are not orchestrated by human hand, but arise from the underlying spatial distribution and motions of matter. By tagging and tracing the progenitors of a particular bright galaxy at the present epoch, one can reconstruct its merger tree, a branching history of all the halos and smaller systems that merge to form it, complete with timestamps, mass ratios, and orbital parameters, allowing detailed connections to be drawn between specific classes of present-day galaxies and the incidence and timing of their past collisions. Every improvement in observational capability feeds back into these models. When deeper surveys uncover, for instance, surprisingly massive disk galaxies at a time when the universe was only a couple of billion years old, largely unscathed by major disturbances, theorists must adjust prescriptions for how rapidly mergers occur and how robust disks are against disruption. Conversely, when wide-field imaging of nearby galaxies reveals ubiquitous faint streams and shells, models must provide enough minor encounters to account for this debris. The iterative dialogue between simulation and observation thus uses the byproducts of collisions: tails, rings, shells, thickened disks, compact remnants. Not merely as curiosities, but as calibration points for the entire edifice of cosmic structure formation. Even at the scale of clusters, where collisions between the largest gravitationally bound systems in the universe release energies that dwarf those of galaxy-galaxy encounters, subtler processes akin to their smaller-scale cousins occur. So-called jellyfish galaxies, identified in clusters like Abell 2744 and others, display elongated, tendril-like streams of ionized gas trailing behind them as they plunge through the intracluster medium, their own interstellar gas being stripped by the combination of ram pressure and tidal forces. In some of these tails, star formation lights up, producing strings of young stellar knots that will forever be left behind as the parent galaxy speeds onward, a dramatic illustration of how the combination of collisions, environment, and hydrodynamics can literally peel the gaseous skin from a galaxy, exposing a gas-poor, quiescent remnant that may later resemble an S0 or elliptical. In extreme cluster mergers such as the Sausage and El Gordo systems, shock fronts driven through the intracluster gas by the collision travel over megaparsec scales, heating electrons to relativistic speeds and lighting up the radio sky with vast arc-shaped relics. Although these are not galaxy-galaxy collisions in the classical sense, the galaxies plunging through these cauldrons do not emerge unscathed. The abrupt changes in external pressure and the enhanced turbulence in the ambient medium can strip and compress gas, trigger brief star formation episodes, or truncate them and alter galaxy orbits within the cluster. Thus, even the largest collisions cascade down through the hierarchy, influencing encounters and internal evolution at every smaller scale, from entire galaxy populations down to the interstellar medium of single disks. Behind all of this detail lies a simple but profound shift in perspective. Where earlier ages saw the night sky as a static tableau or, at most, a clockwork of repeating planetary motions, we now perceive it as a dynamic tapestry of structures assembling, colliding and transforming, governed by the same fundamental laws of physics that operate in laboratories and in everyday experience, but playing out on stages and timescales that stretch human imagination. Galaxy collisions, once unimaginable, have become one of the clearest expressions of this restless universe, and every new instrument, every deeper survey, every refined simulation adds fresh threads to the story, inviting us to follow the paths of starlight and gas as they weave together, tear apart and weave again in the ongoing drama of cosmic evolution.